Log on, tune in, find out. Another good idea from Cambridge.
Friend, soccer coach, and UBC Professor Jim Bryan, and the title is The Motive of the Commuting Variety and Related Problems.
All right, thanks for the invite. Yeah, I mean, soccer coach is definitely an exaggeration. My 7-year-old's team lost, I think we were 27-1, 1-27. Sorry, so we won one game, lost 27. So I've been fired from as my coach of my 7-year-old. I like to start with a problem, old problem posed by Fight and Fine in 1960. They asked and answered the following question: what is the probability that two randomly chosen matrices, two random n by n matrices, whose entries are in a finite field with entries in FQ commute? So obviously for any finite field, this is a counting problem. There's a finite number of these. If you want to know the probability, you need to compute the proportion. So let me give you their answer. Let's do a little bit of notation first. I'll write n for n by n matrices, GLN for the invertible ones, let's write Cn for the set of commuting matrices. And let's see, maybe I'll just do this for a number of elements in the set. So, okay, so just to warm up for this problem here, of course, it's easy to count the number of matrices. That's q to the n squared. It's even pretty easy to count the number of invertible matrices. First column has to be a non-zero vector. The second column should be a vector that's not in the span of the first one. Second one, third one should be not in the span of the first two, etc. In fact, just since we're warming up for this probability, that shows you that if I divide that formula by that formula, you get the probability that a random matrix is invertible. These guys will show up in this formula. So what did Fight and Fine do? They counted this, so they figured out.
Can I ask a stupid question? So you're taking the uniform distribution on the
yeah, I am.
of the matrix.
That's right.
Is that invariant under the adjoint action?
Is that invariant under the adjoint
That's a
action?
sensible thing to do. I appreciate I'm ruining your talk.
I think it's invariant if you take into account stabilizers, I guess. I mean, it doesn't, right? That action has, by conjugation, yeah, has
If I
stabilizers.
change basis, I'll still get the uniform.
I'll just say yes to that. I think yes. I don't know. I mean, you could probably guess I'm not really interested in probability here. You know, I gave a similar talk where I put at UBC where I put we have all these probabilists at UBC. So I intentionally put this probability into the title to try and get all the probabilists to come, and then quickly shift to motives. But actually, none of them showed. Yeah, they weren't. they weren't fooled anyway. All right. So what does the theorem say? Okay, so it's the following sum. So these probabilities show up. So this is a sum over partitions of n, where I write a partition. The bk's are the number of ones, so the number of k's in the partition. Okay. So it's a sum over the partitions of n. It's this product then. Bk is the number of parts of size k in the partition, and we have this. Okay, so that's the solution. And I guess one thing that's not obvious at all from this, the way this is written, is this is actually a polynomial in Q with integral coefficients. Okay, so their method for proving this was actually quite complicated. But if you look closely what they're doing, their method gives a stratification. I would claim kind of the wrong stratification, but a stratification nonetheless, a stratification of this commuting variety into strata which all look like affine spaces. So an affine paving. So I've got some index set indexing the strata, and each strata is just an affine space over FQ of some dimension. So of course, if you're now counting points of a finite set, and I've split my set up into a bunch of things that look like this, it's very easy to count the points here. That's just a copy of Q to the AI, and so you get a sum of that. So that's, of course, why this is a polynomial in Q. In particular, it says that they've actually proven a formula in the Grothendieck group of varieties. So we get a formula So let me just remind you what the Grothendieck group is. So K0 bar K, this is the free abelian group. Generated by isomorphism classes of varieties over K. So we'll denote that by isomorphism classes of varieties. With the relation that says that really all we care about varieties is up to stratification. So I'm allowed to pull it apart by closed sets. So if Z is a closed subvariety, then I can pull it out, and the motive is the motivic class. We'll call the elements here motivic classes, is the sum of the motivic classes of each of these. So in particular, if you have a stratification, it's the sum of the classes of the strata. Yeah.
Just to be sure, I mean that identity implies that that's polynomial on Q with positive integral coefficients.
Yeah, right. So
that's
this
also true, right?
What?
That actually the coefficients are not negative also. Then. Okay.
Yeah, that's right. With integral, in fact, positive coefficients. That's right. Yeah. And in fact, this is a ring under multiplication, under Cartesian product. Okay, so in fact, let's rewrite this just in that language. So we'll replace, these are all varieties, of course. So we'll replace counting my classes. And I will we'll write Q for the mode of the affine line. Yeah, okay. And so, all right, so what's the goal of this talk here is to give a different proof, a simple, a better proof of this formula maybe. It's in a way that generalizes to some related cases that are of interest to us. So in fact, I'm going to now work with the complex numbers. Part of the reason that their proof was kind of complicated was that they were working over this finite field and didn't have things like Jordan normal form. Let me just give you, so why am I interested in this? All right, so the goal of the talk, so reprove this in a way that so refines and generalizes the and in some sense, the motivation for this talk from the point of view of this conference will come at the end, where I'll explain how the things I'm computing are related to Donaldson-Thomas invariance. But you could also take the point of view that this is sort of a basic object in algebraic geometry, the commuting variety and related things, and worthy of study in its own right. So just to give you a flavor from that point of view of a generalization, of a new result, and this is all work with Andrew Morrison. So we could get one refinement. So let's define, all right, so let's fix a partition now. Once again, I'll call bk the number of k's in the partition, number of parts of size k. And now we can define a variety where, okay, so once again, A and B commute, but now A has Jordan type given by lambda, or by, so I called it alpha, by alpha, given by alpha. Okay, so you can look at the variety of commuting pairs where one of them has a fixed partition when we put it into Jordan normal form. And then the result, so the theorem's going to be on two boards. As you might guess from this formula, which is a sum over partitions, each of those terms correspond to the motives of this thing. So the motivic class is just this GL. And okay. And that's somehow not at all obvious from Feit and Fein's affine paving, because like I said, they don't have, on the finite field, they don't have Jordan normal form. They have a very different thing. And that particular form that they get comes after a fairly extensive amount of combinatorics. Okay. So anyway, we'll see how things like this fall out fairly easily.
Jim, is end?
What's that?
L
Oh, yeah, thank you. L is, equals L.
Is n divisible by GLN? Or does this only make sense when you take the...
No, I mean, n is just q to the n, right? And q to the n squared. So it's not, right? And once again, this isn't sort of obviously a polynomial. But
GLN is divisible by the product.
yeah, this GLN and then these, yeah, I think there's enough in here to cancel this.
Yeah, of course.
Yeah, so I think this one is obviously a polynomial. Maybe the other one is obviously a polynomial. Anyway, oh, because that's a product, yeah. Anyway, okay. All right, so let's do this. So first thing we should do, so I'm just going to focus on reproving that one, and then we'll discuss the generalizations at the end. So let's sum this into a generating function. All right, so just a mixed notation a little bit, but when the argument is a t, this is the generating function. So by definition, this is. All right, so I'm going to normalize. Well, let me just do this formally first, and then we'll discuss. So if we just use their formula there, this is now some. Okay, that's just dividing that formula by GLN, multiplying both sides by t to the n, and then summing, and then we can just have fun. Normally suppressed, but I like doing it, so let's switch those guys. Okay, we have this thing, and now, yeah, so I can write that explicitly. Oh yeah, see, because this, remember that factor was this thing. And then Euler's formula, there's an Euler's formula that tells you what to do with that sum. So this is from a formula due to Euler that says that that sum is actually a product. So this is from Euler's formula. Okay, so in fact, this is what we have, but I want to think a little bit about where is this formula taking place? What have we done? We did something formal, but where does this formula actually live? So it's a power series, a formal power series in T with coefficients. Well, the first thing I did was I divided by GLN. So actually my coefficients are, I'm taking this Grothendieck group, but I had to invert the class of GLN, which you can do by inverting these classes. Okay, that's one thing I did. Something else I did was, in order to employ Euler's theorem, which has told me how to take this guy right here and write it like a product, I want to view these rational functions in their Laurent expansion in L inverse. So I'm actually viewing this guy sitting inside K0 var, where I'm taking Laurent series in L inverse. Okay, so this is the ring where this formula is making sense, and this guy right here, this is the by a theorem of Tohen and Ekdahl. This guy right here is the same as the Grothendieck group of stacks with affine, algebraic stacks with affine stabilizers. Okay, so it's telling us we should view this guy, we should view the objects over here, these things, Cn over GLN perhaps instead as a stack. The natural formula comes when you sum not the commuting varieties, but the commuting varieties divided by the GLN.
What do you mean by affine stabilizer?
The stabilizer are all affine groups. Yeah. In fact, you can assume they're all GLN for some n. Right, so this formal quotient that I made.
I'm sorry, what is affine group?
Affine algebraic group.
What group?
Group given by an affine variety, GLN.
Which is affine, which is algebraic group, which is an affine variety?
Yeah, I think so, right? Yeah. So this formal quotient that I did over in this ring viewed in here is actually the class of the stack quotient. Stack quotient. And so this is maybe a better object to think about. And of course, it's easy to see this is a very nice object. So let's think about it algebraically and geometrically here. So I have pairs of matrices where I'm taking the stack quotient by the action of conjugation. So I can view that as the stack of modules of length n over the ring CXY. So this is modules of length n.
On that equality on that board, on the left-hand side, there's no action specified. Are you saying that no matter what action you put, the quote the
Yeah, because this is a free action. I mean, there's a little bit of dancing one has to do to first of all define the Grothendieck group of stacks and then prove a result. The kind of result you want is that if you have a fiber bundle which is trivial in the Zariski topology, then the Grothendieck group, the element in the Grothendieck group is of the total space is the product times the base, and these are these sort of by caveat. This is a locally trivial in the Zariski topology bundle over the quotient. So Cn is a locally trivial bundle over this stack quotient with fibers that. So that's what this formula is.
The action is just by conjugation.
The action is by conjugation, yeah.
That's free.
Yeah.
It's not free.
No, it's not free. That's why we're in this stack world. Yeah. Yeah, I mean, in fact it's a pain if you try and think about it like all those stabilizers. That's somehow part of the magic here. Okay. So and then let's see. So what is this? This is easy to see, right? You choose modules of length n. So if I have a module M, I can choose a basis. If it's finite length, this is just then I just get a vector space. And then how do I get to matrices? Well, just A and B in this commuting variety are multiplication by x and y. And this stack quotient is mods out by this choice of a basis. And maybe slightly more geometrically, but equivalent, is we can think of this also, modules over Cn, we can think of this as torsion sheaves on C2. So stack of torsion sheaves, supported at points of length n. So it's torsion sheaves, zero-dimensional length. Yeah. Okay. So we want to think about this geometrically. This formula, the Grothendieck group, is this geometric thing. So we want to think about this formula want to prove this formula geometrically using these geometric descriptions. And there's sort of one tool, and it's not a, it's a bit of a machine, but it's actually a pretty easy machine. It's not a deep machine. Let me introduce it. So the main tool here is power structures. So let me give a definition. A power structure on a ring R, so R is commutative ring with unit, is a map. All right, well, let me Okay, so what is this? This is power series, formal power series in T whose coefficients live in this ring. So this guy is formal power series in T whose constant term is 1, the unit. All right? And it says if I take a formal power series, T, and I take an element from my ring, say M, then a power structure is something that assigns a new formal power series, which we will call A of T to the M. And this should satisfy, so satisfying all the, all the relations that you would expect from exponentiation. So there's 7 of them. I'm actually just going to go ahead and write them down. It's not that bad, but why not? These are all the relations that my calculus students at UBC forget or add new relations to with embarrassing regularity. So we should have that if I raise something to the 0, I get 1. If I raise something to the 1, I get the same thing back. If I take the product of two things, all right, hang in there, there's not too many. This one they always forget for some reason. 5, 6. Okay, now maybe the slightly more interesting things. We want 1 plus t to the m to start like that, and one that takes a few moments to see that it's saying anything at all. Okay, that is a power structure on a ring. Okay, and the, maybe I'll put it over here, so I'm going to keep that formula. The theorem is there's a pretty natural power structure with geometric content on this Grothendieck group. This is a theorem of Gusin-Zade Mella-Hernandez. So there exists a power structure uniquely determined by, and let me just rewrite this one. This is not what it's uniquely determined by, but That's from the formal axioms, but it's uniquely determined by this formula here. Where x is a variety. Okay, so there's a unique way to extend this to general power series whose coefficients are arbitrary element, and to powers which aren't necessarily varieties but are possibly differences of varieties. And in fact, I want to just write the geometric version. So more generally, I mean, this theorem is the theorem, but I want to tell you a version of this in a slightly more general context because we're going to need it. So more generally, if my power series has coefficients which are actually varieties, right? So we're in this Grothendieck group, but in general, those are differences of varieties. Let's say I've got something where the coefficients are all effective, they're actual varieties, and x is a variety.
How far is it from lambda ring?
Sorry? Yeah, this is this structure, this whole, if you're wondering why you haven't heard of power structures before, if you haven't, it's probably because this is really a pre-lambda ring structure. So this language you have heard of, you've probably seen similar things going on with lambda rings. Now the reason I'm formulating in this power structure language is it's easier to state kind of a geometric interpretation of this pre-lambda ring. So the Grothendieck group has a couple different lambda ring structures, and so in particular it has a couple different pre-lambda ring structures, and this is one of them. But I don't need sort of the more difficult axioms of the lambda ring in this context. So, but yeah, this has to do with lambda rings as well. If you have a pre-lambda ring, you get a power structure. But so what's the geometric content? So more generally, varieties and x is a variety, then I can actually say geometrically what a of t under this extension to the x is. So where, maybe I should so where bk, so what is this? This is configurations of AI valued points on X with total charge K. So let me write this in formulas and then I'll draw a picture. So in formulas, this is pairs S phi. So S in X is a finite subset. Phi is a map from S to the disjoint union of the AIs. Those were the given varieties. And by total charge, I mean I look at each of these points in the finite set. Phi then gives me an element in here, and so it lands in one of these components, and we'll call I that component, and I want to sum those i's, and I should get k. And what is this? So, all right, if you haven't yet parsed that, how should you think of this? You've got x, you've got some finite set of points in x. So you can think of this as a bunch of particles running around on x. But the internal state space of so each particle has some charge I, and the internal state space of a charge I particle is given by an element in AI. So these might have particles of various charges and the charge, so AI is the charge I state space, internal state space.
Is AI a variety?
Yeah, so AI, so look up here. So in this case, where I've got this collection of varieties, AIs are varieties, and X is this variety, then this power structure has this geometric interpretation, okay?
You could write this as a product of AIs and X's quotient.
Yeah, so you can write it as a big sum over various diagonals where I've deleted diagonals, right? I mean, these, and yeah, so you can with symmetric groups and whatnot, yeah, dividing out. That's right. I mean, I think, yeah, anyway, that's what it is. So this is the theorem we're going to use, and we're going to use this, well, we're going to use a generalization of it a little bit. But the point I wanted to make actually is there's no geometry in this theorem. All right, so this is, this is this is a set theoretic statement. I mean, there's sort of the way you extend that is unique, and the axioms that you check don't really have anything to do with the geometry of varieties. It's really a set theoretic statement here.
You never have to worry about Zariski local triviality of these things?
Not for this. Not for this theorem. There is I mean, this issue, of course, comes up, and there's one. I'm going to use exactly one geometric statement, which does that, which does need that. So that was coming to my next point. So this theorem is set theoretic. No geometry. I mean, even though we've given this kind of geometric interpretation, and it's pretty easy to see these hold and to extend it. And in fact, we need a single geometric statement. And this is due to Taro. Taro. Okay, sorry. Taro. That's still wrong. There we go. Taro, sorry. But yeah, sorry about the name. Thanks for the theorem. Yeah, all right. Or the lemma, I guess. I mean, yeah. So he proves that, well, okay, so yeah, so this statement holds in the Grothendieck group of varieties. So when k is equal to 1, this is something you're familiar with, right? The symmetric product of A1 is AN. And of course, when k is not 1, this is not an isomorphism of varieties. But in the Grothendieck group, this still holds. Okay, and I need a lemma, okay, that soups this guy up to this Grothendieck group. The stack of Grothendieck groups. So the power structure uniquely extends and in fact, so remember we're viewing the Grothendieck group of stacks as sitting inside of these Laurent series, because that's where we're going to end up writing everything, such that I'm going to run out of room. Hold on. So if I raise now, I'm allowed to raise something to the negative power. Okay. And, you know, this statement right here, oh, yeah, I should have written that. Okay, so let me write this. Okay, so I should have written this before. So if I change the pluses on change the minuses on the k to plus, okay, then this statement right here is equivalent to the statement I just wrote, but with the pluses. Okay, that's just remember from the symmetric product. That's what that says. And there's a unique way of extending it to these negative powers such that the same formula holds. Okay, so you can think of that as saying something weird about the symmetric product of 1 over L. Okay.
You also have to assume some sort of infinite version of x to the a plus b equals x to the a, x to the b.
X to the A, no, where,
How do you expand an infinite power, an actual power series in the exponent?
Yeah, right. You do need, that's right. You need to be able to say that if I have a formal series in the exponent, that I get a formal product. I mean, but you get an infinite product. Where is it? Yeah. But that's okay. They all start with 1, right? So then if I look at any term, everything's still in the right ring. Okay. All right, let's get. Okay, so let's just actually prove this, reprove this fine result using this stuff. So this is a very simple argument. Actually, and the same kind of argument has appeared in some other contexts. Kontsevich, Soibelman have a similar kind of idea. It appears in the context of the cohomological Hall algebra using the Harrison complex. So they don't have the power structures, but it's probably all the same thing. I don't know. All right, so here's what we're trying to do. Remember, we're trying to understand this guy. And now we're viewing those commuting varieties where we've renormalized, but the group is actually the stack of torsion sheaves. Oh, I meant to say one other thing. Extends. And, very important, and this geometric interpretation of the power structure continues to hold. So this exactly what I wrote holds. Geometric interpretation holds when the given AIs are stacks and X is a variety. Okay, so now I'm in this ring of, I'm the Grothendieck ring of stacks. Of course, elements are really differences. So first of all, I want everything to be effective, the AIs and the X, and I want X itself to be a space. The AIs are allowed to be stacks, and then this same word-for-word description of the coefficients of this power series hold.
Does this mean it doesn't extend to K0 stack?
No, it does. The geometric, it's just harder to say what those coefficients. Oh, you mean?
The lemma hold.
No, the problem here is just writing down what the coefficients BK. So there is a unique power structure. So you get this thing, even if these AIs are, even if X is a stack, or these guys are differences of stacks and all that. This is all well defined. This thing right here is a geometric interpretation of these coefficients, and that only works if this guy up here is a variety. But these guys can be stacks.
But you should have affine fibers again.
What?
AI should have affine fibers.
Yeah, well, everything has affine fiber. That's where I'm in. That's the ring I'm in, right? Yeah. Okay. All right. So this is. All right. So cute little calculation here. Let's do it. Okay. Okay, so I can consider torsion sheaves supported at the origin. That's what this guy is. Torsion, or maybe I'll put it over here. Torsion sheaves supported at the origin. And similarly, I'll need torsion sheaves where the x coordinate is 0 and the y coordinate is non-zero. Okay, so this first statement here is that geometric lemma. It says that a torsion sheaf on all of here is just going to be given by a collection of its support, and then we have the length of that module at each support. And no matter where it sits in C2, that internal state space, that internal moduli of the guys supported at that point are given by this stack right here. Okay. And of course, the same argument says that if I take just the guys supported at 0, or sort of on the x-axis or the y-axis, except minus the origin, that this is this guy Oops, that's a 2. At this guy to the C star, right? Because it just moves along that C star. And so now I can just divide, and I get that C of t is so, this is L squared, and this is L minus 1. So I'm just inverting those guys, which I'm allowed to do in this ring. And yeah, and then what is this guy right here? So tracing back through to get to matrices, right? This thing is matrices which commute. So where A, the first one, is supported at 0, so A is nilpotent, and B is invertible because all its eigenvalues are non-zero, divided by the conjugation of GLN. And so, of course, by conjugating A, I can put it into Jordan normal form. So if I write J lambda for the Jordan normal form of a nilpotent matrix corresponding to a partition lambda, so that's just this kind of thing with the parts, right, corresponding to a partition, then what I get is that this is a union over the different possible Jordan normal forms of this J lambda B equals B J lambda. But in order to conjugate A into Jordan normal form, I've lost some of this, so I have to divide by the stabilizer of J lambda in GLN, but which is exactly that. That is, that B is invertible, and this is what it means to be this stabilizer under conjugation, right? So this is just a finite number of points, and it's the number of partitions. So in this formula over here, this is just the generating function of partitions, the number of partitions. And maybe I'll write this one now as a power series as well. So so if I divide top and bottom by L inverse and I make it into a series, like that, and so I get that C of t. Well, this thing right here is famously t to the n to the minus 1. And now I've got, because of this, I've got a product. K goes from 1 to infinity. And I've got L 2 minus K. Starts at 1 and goes down. And so I get, then by that geometric lemma, I get this guy. Which I think I haven't erased yet. That guy. Where I reverse the ends and case. Okay. So, last 10 minutes, let me explain why I'm interested in this. So it goes, it has its origin in this paper that I wrote with Kai and Balish. That says if you're interested in the motivic Donaldson-Thomas invariance of, well, let me write it, of the Hilbert scheme of points on C3. So we've got n point. We can make a generating function out of motivic versions of the Donaldson. This is a Claviau threefold. This is a moduli space. There's motivic versions of the Donaldson-Thomas invariance. Well, that they can be computed in terms of this guy, this commuting variety, as follows. So this is the theorem. Okay, and this has a generalization due to Andrew Morrison. To more general context, let me explain it. And in fact, this is the reason how you get close cousins of these commuting varieties arise. So maybe I'll write his formula and then explain the terms. So the more general setting here is motivic Donaldson-Thomas invariance of a quiver Q with superpotential W and framing F. So there's going to be an analog of this commuting variety here. Analog of this formula, and I'll explain what these guys are. Okay, so what is this? Q is a quiver. Our superpotential for this theorem is assumed to have kind of a special form. It's the product of a linear factor and something else. So superpotential with linear factor. And F is a framing vector, which gives me a stability condition. Okay, what's over here? Oh, and then I guess I should say dt motive is then the generating function for the motivic Donaldson-Thomas invariance, so you could say virtual motives of this quiver. So virtual motives of the quiver with superpotential and stability. Okay, so on this dt side, you have two things that make the story kind of hard, which is that you're dealing with virtual motives, things coming from vanishing cycles of the superpotential, and you have a stability condition, which in practice is hard to deal with. But this generalization, this is kind of a generalized commuting variety, so is a much nicer object. So Q tilde is a reduced quiver. It's when you have this quiver and you have this linear superpotential, then there's a recipe for getting rid of some of these arrows. W tilde here is just this R. So these are giving you relations, and this is now C this C here is a generating function for ordinary motivic classes, ordinary motives, so no virtual motives, of this quiver with relations, now just the relations, and no stability. Okay, so the formula sort of does two things for you from this point of view. Is it takes care of stability and it gets rid of the virtual stuff and gets you in terms of, so, and this is a generalization of that formula in the case, the Hilbert scheme can be given as a quiver with a superpotential, with a framing, with a linear factor, and then you get exactly these commuting varieties.
So F is just a number here?
No, F is a vector of stability, and so, so maybe I should say a couple things. Also this star, I need to say a couple more things. So star.
Is this problem you're allowing strictly semi-stable issues? Or?
Well, all the stability happens over here, and no, when the framing happens, these are stability conditions with no strictly semi-stable. So that's kind of one of the nicest kind of stability conditions you could put. These guys, of course, these are stacks, but these are the ordinary motives, right? So these, okay. And the product, I should say, so one price you pay is that this is, in general, a non-commutative product. Although I should say this still completely determines these invariants once you know these. And it's mildly non-commutative. And in many cases of interest, it actually is just commutative. So what is this guy? This is the usual thing, which is this is L. So we have an Euler form on the vectors on the quiver. And what was else I was going to say? You want to make sense of this guy. So T, there's actually a bunch of variables corresponding to, corresponding to the different edges. So this is some sort of shorthand for just, T1 L to the minus F1 over 2 to, I've got some number of vertices.
Are there some examples where the C has the exact formula?
Yeah, so right. So where are there some exact formulas? So examples, the ones that arise from the DT invariance of this orbifold. So here G is a finite subgroup of SU2. This machinery all goes through, and in fact, then these Euler products are commutative, and so you can just divide both sides there. And in particular, in the case of this argument that I gave, this sort of very simple argument that produced this guy, also works in the case, so commuting varieties. Can be computed by the above method, at least for the case of G equals Cn. So there, it's a similar kind of problem, but now my commuting matrices are asked to have certain block forms. So they're A and B are broken up into blocks, and the blocks are put in certain places. And this commuting variety, so a similar kind of argument that we just gave on the board, sort of very cheaply, we'll give these guys right here. Sorry?
What is Q tilde in the
What is the what?
Q tilde in quiver?
Yeah, what is the, okay, so it's, okay, yeah, so the quiver here with the framing is something like, yeah, so you get arrows, two directions, so this is the full guy. And then the reduced quiver, so there's different ways to reduce it. You'd have to reduce it the right way in order to use that formula, but is you erase these guys. So you keep the loops and you erase half of these guys, and this, of course, goes away. I think there's a loop here, too. So this is the reduced quiver. For A5 or whatever.
The product is really inner product?
Where you're asking about this product right here?
The linear factor.
The linear factor.
W equals L.
This.
Yeah. Really inner product?
Yeah, I mean product. This is written in the path algebra, right? Yeah, inner product.
If it is in the product, then the W tilde is not just one function, right? It should be like a several.
Well, yeah, no, I'm writing the W, not the trace of W. Is that what you're asking about? I guess I'm writing the.
I'm just curious why the reduced one is Calabi-Yau algebra. I mean,
No, it's not. It's not. So the reduced guy is not Calabi-Yau.
Then usually, what does W tilde mean? It's a couple of relations.
Yeah. So this is the generating function of ordinary motive. I mean, I should have written that. So generating function for the ordinary motive of the quiver variety with relations. So these you now just apply the relations with relations.
You really can't write W tilde, actually W.
Oh, all right. I can't write W tilde. Okay, all right, yeah, so that's right. Maybe this is bad notation. In fact, this I changed from Andrew's paper. So Andrew probably has the right notation. Yeah, I mean, can I just say what I mean? Yeah, I mean the quiver with these relations. So no superpotential anymore. I'm not taking trace and derivatives and stuff. I just want that relation. Yeah, that R. Anyway, thank you. I'll stop here.
I guess people are hungry and we have a press schedule, so perhaps one or two quick questions for lunch. Good. No good.
How's your calculation, how it's related to Knudsen, Hansen, and Stem?
How's it related to what?
Knudsen, Hansen, just interesting calculation of degree of this variety.
Yeah, the degree. I don't know how the motives are related to the degree. Is that the question, the degree of the commuting variety? How's it related?
There's some integrable system.
Yeah, and Knudsen also studies this sort of almost commuting variety where the commutator is something diagonal. And I don't really know how to put that into this language. So I mean, obviously there's a lot of work been done on the commuting variety and a lot of open questions, like we don't even know if it's reduced or not. And this Grothendieck group is sort of insensitive to all of that, and this doesn't really, as far as I can tell, say anything, but, and I couldn't see how to use any of the results. I asked all those, but yeah, anyway. Yeah, so I don't know there's any relation with that.
Is it correct to think of this argument, that you've given as some way of organizing the process of stratifying by eigenvalues?
Yeah, I think so, but if you try and do that by hand, which is what we did, you really contend with the monodromy and the symmetric product. So that sort of obvious stratification uses symmetric product. So I think what's going on is Bert's lemma, together with this power structure, organizes all that stuff, which just looks like a nightmare when you have to do it by hand. So that's kind of the way I view this, is some sort of organization of what would be an obvious stratification, but one that's hard to deal with because you don't have locally trivial fibrations. You've got all this monodromy everywhere. But all that monodromy is always built into that, always looks like symmetric products. And so this somehow excises all that. Yeah.
Okay, it's just let's thank the speaker. Go for that.